When artists set up this installation in Seoul, they arranged photographs of clouds into a massive grid. They ran these through facial recognition software. It analyzed the water vapor and confidently flagged a match. It detected human faces staring back. It's tempting to assume the AI was hallucinating or that the software was simply broken. But the entire system was operating perfectly. The program was executing its mathematical instructions exactly as designed, without a single error in its source code. An AI does not actually look at a picture and see a cloud or a face. It only calculates the statistical patterns we have trained it to look for. We often talk about artificial intelligence as if it possesses cognitive understanding, like a digital brain that comprehends context. In reality, it is a statistical pattern matching engine. It takes raw, unorganized inputs, filters them, and outputs a probability score. This process happens at a scale and speed difficult to grasp, sorting millions of variables in fractions of a second to find hidden structures. Because the machine relies entirely on the information it is given to build those structures, its accuracy and its fairness are strictly dictated by its training data. To understand how an AI learns to misinterpret a cloud, or how it learns human bias, we have to reverse engineer the stages of its creation. We can start by drawing a line between basic automation and actual machine learning. Automation relies on strict, rigid instructions. If a car wash timer hits 5 minutes, the water shuts off. That works in a controlled environment. But if you introduce an unexpected variable, like an oversized truck, those fixed rules break down. The system cannot adapt. Artificial intelligence replaces fixed if-then rules with dynamic predictive models. Instead of a timer, sensors capture unstructured data, the specific size of the vehicle, the exact level of dirt on the windshield. Rather than being told exactly what to do by a programmer, the AI compares this new data against thousands of past examples to output a specific decision. True AI isn't following static instructions. It is calculating probabilities based on historical experience. That historical experience is built during the AI project lifecycle. It begins by defining a specific problem to solve and then collecting the relevant data to teach the system. This raw data requires preparation. Missing values are filled and duplicate entries are stripped out to create a clean foundation. Let's look at a concrete predictive modeling scenario. Suppose a school wants to guess whether a student will score over 75% on an upcoming exam. They compile data on past students, study hours, attendance records, and past test scores. During the model training phase, the algorithm maps these inputs against known outcomes. It searches for hidden correlations, noticing perhaps that high attendance strongly correlates with high scores. This training process generates a mathematical boundary. The system draws a dividing line through the data to calculate the probability of a future student's success. Before this system is deployed, it undergoes model evaluation. It is tested against new, unseen student data to verify its accuracy. Once deployed, this model is simply a reflection of the students it studied.
If the training data is flawed, the model's logic is flawed right along with it. This exposes the core vulnerability of all machine learning, the principle of garbage in, garbage out. Consider an AI trained to recognize sports equipment. If the dataset contains 10,000 images of cricket bats, but only 50 images of badminton rackets, the data is severely unbalanced. When you introduce a new, ambiguous image, the system doesn't guess evenly. The sheer weight of the cricket bat examples skews the statistical probability, pulling the prediction aggressively toward the overrepresented category. This mathematical flaw is exactly what happened with the clouds in Seoul. The facial recognition software was trained on a dataset that heavily overrepresented specific demographics, primarily light-skinned males. Because of that data skew, the AI was primed to look for that exact facial structure. It misinterpreted the random ambient noise in the clouds as the pattern it had been heavily trained to find. This exact same flaw corrupts text, too, through natural language processing. If you enter the gender-neutral Hindi phrase, "Vah doctor hai," into an automatic translator, the English output will frequently default to "he is a doctor." The system learned a gender stereotype. In the massive historical text datasets used to train it, male pronouns appeared near the word doctor far more frequently than female pronouns. An AI does not invent bias. It acts as an unblinking mirror,
mathematically amplifying the historical imbalances already hidden within our records. Deployment is not the end of the AI lifecycle. When a model hits the real world, its job is just beginning. Over time, real-world parameters inevitably shift away from historical norms. This is a phenomenon known as data drift. If our school completely changes its exam structure, the old historical patterns no longer apply. The predictive model will fail to capture the new reality. This makes continuous monitoring and maintenance essential. Systems must be regularly tested and retrained with fresh, accurate data to maintain their reliability. Because human environments constantly evolve, an AI model is never truly finished. Ongoing human intervention is a permanent requirement. Today, AI is deployed to make critical decisions in high-stakes fields, diagnosing patients in healthcare, approving loans in banking, and assessing risk in law. Deploying unbalanced datasets in these sectors carries severe consequences. When demographics are underrepresented in the training data, those specific populations absorb the highest rates of error and real-world harm. This points to the core rule of integration. Algorithms must exist to assist human decision-making, not to replace human judgment entirely. Which brings up the ultimate question of accountability. When a machine makes a dangerous or unfair decision, who is responsible? The responsibility cannot fall on the software. It rests entirely on the developers who build the system and the supervisors who curate its data. In an era increasingly driven by algorithmic prediction, human accountability remains our ultimate and only safeguard.